There's a surprising engineering connection between this 1920s airship and the Hubble Space Telescope. The R-100 airship was built in Britain in the late 1920s and at the time was the largest aircraft in the world. The design team was headed by Wallis, more famous among aviation buffs as the inventor of the bouncing bombs used to destroy German dams during World War II. Wallis and the R-100's design team came up with a new system of geodesically arranged wires to transfer the lift of the gas bags into the frame of the airship. The geodesic lattice of wires was lightweight, resilient, and spread the load of the airship evenly over the delicate gas bags. Wallis later adapted the geodesic lattice idea for use in aeroplane construction by replacing the wires with aluminium beams. Wallis's geodetic airframe had several advantages. Geodetic lattices allow the construction of large but lightweight structures and are also very strong. Another key advantage of geodetic construction is its robustness. If a beam is broken or a section is damaged, the forces carried by the damaged components are redistributed throughout the remaining members, making the structure very resilient. Wallis applied this concept to the design of the Vickers Wellesley and later the Vickers Wellington bomber that served throughout World War II. The Wellington quickly gained a reputation as an aircraft that would get its crews home. Wellingtons managed to limp back to base having sustained damage that would have crippled any other aircraft. Because of this, the Wellington was loved by its crews and by the British Air Ministry. When Wallis tried to borrow a Wellington to test his bouncing bomb prototypes, he was told,
"Even if we made a few dummy bombs, you say you need a Wellington bomber for test drops. They're worth their weight in gold. Do you really think the authorities would lend you one? What possible argument could I put forward to get you a Wellington?"
Well, if you told them that I designed it, do you think that might help?
After the war, the attention of scientists and engineers turned to space. In 1946, astronomer Lyman Spitzer published a paper outlining the benefits of placing a telescope in orbit above the Earth's atmosphere. But it wasn't until the late 1970s that design work began on what would become the Hubble Space Telescope. The forward of the two main structural elements of the Hubble is called the optical telescope assembly, and, like nearly every part of the Space Telescope, represented a major engineering challenge. A major component of this assembly is the metering truss, which had to be rigid enough to hold the telescope optics in the correct alignment, and it had to do this through the extreme temperature changes caused when the Hubble passes through Earth's shadow. The metering truss is quite large. It's nearly 5 meters long and 2.7 meters in diameter. And being part of a spacecraft, it needed to be as lightweight as possible, but still strong enough to stand up to the forces of a rocket launch. The Hubble's engineers used Wallis's geodetic airframe ideas to design the metering truss, which they built out of carbon fibre. Geodetic construction was the only technique that would produce a structure with the size, strength, weight and robustness parameters that the Hubble required. The geodesic design has since been adapted and applied to other satellites, and is a popular construction method with many architects back on Earth. Geodetic structures are popular in science fiction. Even Dr. Evil's moon base is a geodesic dome. Wallis's geodetic airframe design is an excellent example of how ideas in engineering are adapted in innovative new ways, for applications their inventor might never even have thought of.